Okay, good morning, everyone. My name is Jim Oakes from Super Systems and the past president of MTI. I'd like to welcome you to FNA 2024 technical sessions provided by the Metal Treating Institute and the MTI Education Foundation. Before we introduce the session, I would like to cover a few housekeeping items. First, I would appreciate if everyone would silence their cell phones so as not to distract the presenter and others in the class. FNA is officially videotaping each session for the attendees to view once they've been produced after the conference. We ask everyone to please refrain from taking pictures of the PowerPoint slides or videoing the presentation. If we see anyone taking pictures or video during the presentation, we'll ask you to put your cameras away. Please be respectful of this request. Lastly, there are QR codes on the walls that are going to be used for surveying the sessions. Once the session is over, we would appreciate taking a few moments to complete the very brief survey. This will help us for future programming. Each session survey that you've completed and you'll be entered into a drawing for a $100 Amazon gift card. Now for our session. How to reduce labor cost through furnace optimization and automation. A presentation on ways to optimize your furnace to improve throughput, reduce labor costs associated with running heat treat furnaces. Help me please welcome our speaker, Mr. Matt Clinite.
So I am Matt Clinite. I'm the Director of ICS Sales and Retrofits at Ipsen. And when I sat down and thought about what topic I wanted to present on, I wanted something that related to everybody, that could cast a wide net and be applicable to everyone who's attending the conference. I think I've done that. There's a lot of people in this room. And this is my fourth time, by the way, I think, presenting at FNA, so I'm excited for this. And I was told last year I had the highest attendance in my room. I think I might be going 2 years running, so I'm pretty excited about that. Thank you for helping with that. But yeah, today we're going to talk about ways to reduce cost when operating furnaces and heat treating. So we're going to talk about ways to increase quality, efficiency, and speed while reducing costs through automation, furnace design, and recipe optimization. So if you're sitting here thinking, hey, I have to invest a lot of money to realize some of this, you don't. Some of this you can do right now through optimizing the recipes that you're already running in your furnaces. So what is automation in its most basic form? And I know they say don't use the word in its definition, but I feel like you kind of have to in this case. It's to take a historically manual process and to make it automatic. So if we think about it in its most basic form, and we think about early heat treatment, we go back 50 years, and you've got timers on your vacuum furnaces, right? You need to austentize for an hour, or 90 minutes, or whatever it is, depending on what you're doing, until you get to that, fully soak out your parts. The timer goes off, the operator comes over, and he advances the parts into a quench, right? This can be done in atmosphere furnaces, vacuum furnaces, you name it. But in the past, that's the way it was done. It was done through a very manual process. Today, we don't have any of that. Today, we load parts into a furnace, whether it's a batch IQ, whether it's a vacuum, we hit start, and when we come back, those parts are done. And there's almost no operator interface from start to finish. So that's its most basic form when we talk about automation. It's taking little pieces of things that people used to have to do and making it happen in an automated fashion with nobody there to make it happen. Now, automation on its most extreme example can be totally lights out. It can be things like robots racking parts into fixtures. It can be, hey, my parts come in a normalized state and they have scale and they need to be blasted, and maybe the blasting is automated, followed by automated racking, followed by automated heat treatment, you name it. So full automation can be very involved. So I'm going to start with maybe the most extreme example of automation here. And what you're seeing here on the left, you're seeing a ultrasonic washer to make sure the parts are ultra clean before they go into the heat treatment process. You're seeing a vacuum nitriding furnace, a vacuum oil quench furnace, a vacuum gas quench furnace, a post washer, a dip spray washer there in the bottom right, along with all of these tray tables right here, these storage tables. And so this is an example of a very extreme version of automation. This is taking a lot of very different equipment, potentially different load sizes, different hearth heights, you name it, and automating it so that you can have a full lights out system where you just have one operator feeding in green parts, and when they're coming out, they're totally finished. You could add tempers to this line. You could do pretty much anything. So, if you're thinking about, hey, maybe I'm expanding into a greenfield facility and I'm going to put in new equipment, this is something you should consider. Now, if you guys are sitting there thinking, I've got equipment in all different buildings of all different sizes and configurations all over the place, maybe this isn't possible. But if you are starting from scratch, it's something to give some thought to. This is another example of an automated line here in the U.S. This line is a little bit more simple. It is lights out automated. However, it's all the exact same equipment, left to right. This particular company has several of these lines in different buildings, and in each case, it's the exact same furnace over and over and over. But it does have the same lights out characteristics as the other line. It just doesn't have any upstream or downstream processing like the upstream washing, downstream washing, or anything like that. Not needed here because these are 6-bar gas quenching furnaces, but there might be a pre-wash before the parts are going into that, which is not part of this automation. This is just a side view here. You can kind of see the tracks in the floor. That's how the automatic loader operates, going up and down the tracks. There's proximity switches along the tracks. They're going to tell the doors when the cart is in position, when it should open the door, when it's clear of the door so that it can open, and that sort of thing, so they know where the position of the load cart is. And then this is just a rear view here. And you can see that each furnace has its own local controls, but it's also capable of being controlled outside the installation through automation. And you can still access the back here for maintenance. If you have to do any kind of pump maintenance or anything like that, you can still get to it without interfering with the load cart in the front. This is maybe a less automated line here. This one only has automated loading. So this is not any automatic operation of the furnaces. This is simply an operator saying, hey, go to furnace number 3 and load it, go to furnace number 4 and unload it. But it's not actually starting any processing of the parts. It is just strictly for loading and unloading, and the operator has to go to each furnace and start and stop the cycles. So, all right, so some of the biggest advantages of lights out operation. The biggest one is reduction in labor costs. So we see that operators can typically operate up to 10 furnaces at once, and most of that time is just spent fixturing parts. So that's one of the biggest advantages. One of the other things that's a good benefit of it is error proofing, right? Everything is done through barcode scanners. Everything is done through technology rather than an operator having to go to the screen and push a cycle and risking that they maybe hit the wrong cycle or start the wrong process, right? We've had people that have put parts in and accidentally run a burnout cycle and melted their parts. So through having this automation, it really does error-proof a lot of the things that could go wrong. One of the other big benefits, right, is that the furnace loader, as soon as a furnace is open, it's going to load that furnace. So you're never going to have furnaces sitting idle. As long as you have green parts that are on the tray tables waiting for the loader, the system's going to load it as fast as it possibly can. And this is where we see a lot of downtime with our customers that do have operators loading furnaces. You walk by and a furnace is sitting open, and you walk by an hour later and it's still sitting open. And you wonder to yourself, okay, why is that furnace not running parts right now? Well, in this case, if you walk by and there's no green parts on the tray tables, you know right away, oh, shoot, I need to get parts there so the system can do its job. So that's a big advantage to this too. Another one is safety. There's a lot of accidents that happen with forklift travel, with loaders, with doors, all sorts of things, right? And if you have an automatic line with a fenced-in area where operators can't go and it's protected with light curtains in case an operator does go into that area, then you're going to have a much safer operation generally than if you have a manual operation. And then the operator-free part. So we think about this like, hey, there's an operator running 10 furnaces. That's great. There's a big savings there. Think about when the furnace can operate or the system can operate all by itself with no operator there. Think about starting it at night when you don't have a third shift. Think about running it over the weekend when no one's in the building. So this is where we see a really, really big cost savings is where people have these systems where they're comfortable with it. and they run them nights and weekends. They load up the tray tables, and when they leave, they come back on Monday, and maybe they've got 12 or 14 or 16 loads ran with nobody there. So that's a really big savings. Okay, so you're thinking to yourself, I don't have a greenfield facility. I'm not putting in new machines. I don't have a business case right now to put in full automation. What are some other things I can do to reduce costs? So one of those things is a SCADA system. And for those of you that haven't heard that term, it's kind of a broadly used term, but it stands for Supervisory Control and Data Acquisition. And there's different versions of this. Some people just have data acquisition and they call it a SCADA system. But the C in it does stand for control, so if you're not actually pushing control to the furnaces, it's more of just a data acquisition system. But there's a lot of benefits to this too. So one of the biggest advantages is a single database for all of your recipes. So if you've got 10 furnaces or 12 furnaces or 15 furnaces, and you spend a lot of time going to each furnace and making changes to recipes, and then you're not sure, a couple of years pass, and this one has a slightly different version of the recipe than this one over here, and you're constantly doing all these edits, this is one of the places that a SCADA system really shines because we have one central database for all our recipes. So you make a change in that database, and it pulls to all the furnaces. So when that furnace goes to load the recipe, it's just pulling from that one database, and you don't have different versions of the recipe. Another one is going to be real-time process monitoring, right? So let's say you do have a lot of furnaces, especially if they're not in a nice, neat installation and they're all over the building, and you want to see which of my furnaces are running right now, which of them are in cycle, which of them are not in cycle, where are they at, how long do I have until I need to go unload parts. This SCADA system, you can have it set up with a trend screen, you can get a 75-inch TV and have a trend screen on it at all times and see exactly where each one of your furnaces is in the cycle, which ones are open, which ones are going to be coming due soon, so that you can try to improve your throughput and the turn time of unloading and loading your furnaces. Process run data storage redundancy. So for those of you guys in the room who process maybe aerospace parts or medical parts, and perhaps you have to keep records of those process runs, well, if the only place you're storing a record of that run is at your machine and the hard drive goes corrupt, you're going to end up in a bad situation. So by having a SCADA system, you can have all that data stored at the machine, and you can also have it stored on the hard drive of the SCADA system, so you have it in two places in case anything does ever corrupt, then you don't lose that data. And then downloading QC reports remotely. So if you're someone who has to download QC reports and give them to your customers, if you're a commercial heat treater, or even if you're a captive heat treater and you're sending parts off to someone else and you have to provide the run data, you can very easily print the QC data from the SCADA system, put it in with the parts, and be good to go. And this is good for a lot of people. If you think about the people that this affects, this is not one engineer over heat treatment or brazing who's using this. This is the engineer in charge, this is the quality manager, this might be the shipping person, this could be so many people could be tied into this system that it could be beneficial to improve the operations. All right, SCADA systems and NADCAP. Can I see show of hands who's involved with any aerospace or NADCAP parts? There's a lot of people in here, right? So there's some tedious parts of staying in compliance with that. And we hear from auditors and our friends in the industry that a lot of people do it through very manual processes. So all of that can be incorporated into a SCADA system. So for example, calibration due dates and SATs and TUSs, temperature uniformity surveys, your due dates and your results of all of that can be saved in your SCADA system. So an auditor comes in and says, show me the last time you did all this. And you just go to the SCADA, and it's all right there. I can see when I did all these things. I can see the results. All of the results are in a CSV unalterable format, which is compliant, and you're going to be good to go. The other cool thing is all of the, let's say, requirement due dates will remind the operator a couple days in advance, and then we'll lock out the furnace when it comes due, so you can't accidentally run parts when your furnace is not in compliance. Now, you can override that with a supervisor password, so it's not that we're going to shut down your operations, but it's a good way that you don't accidentally run parts when your furnace would be out of the due dates for those. And then I skipped over the second one there. That was intentional. So there's one section that came about sometime in the last few revisions of AMS 2750, and that has to do with thermocouple reuse. I think they call it TUS sensor reuse and SAT reuse, but it has to do with how many times you can use a thermocouple over a specific temperature. And don't quote me on this, but I think for most people, you can use a thermocouple 1 time over 2,300, 10 times over 2,200, or for 3 months, 90 times between 1,800 and 2,200, but not to exceed 3 months, and so on and so forth. And it gets a little bit more grace as you go lower in temperature. So how on earth do you keep track of how many times you've ran those thermocouples at those temperatures? That's an extremely manual process for most people. In the SCADA system, it keeps track of that for you. So on this screen right here, it will say how many times you've used each thermocouple, at what temperature you've used each thermocouple, the last date that you've replaced them, and when it's coming due. So the furnace, the SCADA system will keep track of that for all of your furnaces, and it will throw you a flag, and it'll do the same thing. It'll lock you out of the furnace, and it'll say, hey, you're going to be in a non-compliant situation here if you don't replace your thermocouples. And then it's as simple as you put the new ones in, and you reset the timer, and it goes back to 0 uses and day 1 of that 3-month period. So to me, that's another really smart way. And you're wondering, okay, how does this save money? Think about the time spent tracking all of that. Your people spend a lot of time with that. This system does it for you, and you don't have to think about it. So that's really where the time savings is here, not to mention the risk reduction with not potentially scrapping parts or running them in a non-compliant state. Okay, so you don't have money or a site to put in full automation. Maybe you don't have money for a SCADA system right now. What can I do today when I go back to my plant to save some money in my operations? And that's what we're going to talk about here. So just looking at your current recipes and trying to eliminate wasted steps and wasted time can give you a lot more capacity, a lot more throughput, and lower the cost of running parts. So we're going to talk about, ramp rates. We are going to talk about step heating. We're going to talk about convection heating. We're going to talk about proper use of VRTs and making sure you're maximizing your heating potential. And along with that, digital power control units, guaranteed soak functions, a little bit on cooling rates, and then how to combine sequential heat treat operations into a single recipe. And all of those things are going to be things that you can implement right now at your facility to save time and money. So, all right, if we look at this run right here, this is a pretty typical run. We have a number of steps here where we're allowing the parts to come up to temperature so that, and the reason we do that is we don't want to add too much stress to the parts, right? If we just heat straight up to our maximum critical soak temperature, our parts are going to lag way behind. The parts on the outside are going to be much hotter, and they're going to come into temperature much faster than the parts on the inside of the load, and that's the reason that we add these steps. However, in this case, you can see that first one has a very long tail to it, okay? So it's coming into temperature pretty quick, and then it's just creeping in very, very slowly. And one of the reasons that is this customer has their first step at 850 degrees Fahrenheit. Vacuum furnaces are not in radiant heat at 850 degrees Fahrenheit. So they heat extremely slowly. Anybody ever try to do an H900 in a vacuum furnace and it takes a long time? This is even lower than that. So they really shouldn't have their first step this low. It's a waste of time. Now, if they wanted to have a little one and wait maybe an hour or so, okay. But they're waiting 4 hours for their parts to come into temperature, and these are parts we're taking to 2,000 degrees. So this step should be more at like 1,100 degrees. And it would come into temperature a whole lot faster at 1,100 than it will at 850 degrees. It's taking them 4 hours in this first leg right now before they advance to the next heating segment. So the next one, they're going from that 850 to 1,750, which is a much more appropriate step. And it's only taking 2 hours to come into the soak temperature. The other thing I'll note here, I don't know if this has a laser. It does have a laser, so I'll step around here. So you can kind of see here that there's maybe a bigger discrepancy when it advances between the set point and the actual temperature, and then here it's a little bit tighter. So I'll go over that in a few minutes, but in the recipe you can say how close you want the work thermocouples to be to the set point before it advances to the next segment. And that's what they're doing there. They're giving it a little bit more grace on the first one because we're not anywhere near a critical temperature. And then on this last one, they're going to go to their critical temperature, so they want the parts as evenly soaked in as possible and as close to set point as possible, which is why it's a little bit tighter there. But that's something they can do. They should lift that up to a higher temperature, and to shorten that duration, maybe give it a bigger deadband before it applies heating to the next segment. And then that second one is pretty appropriate, and then they're going to about 2,000 degrees for that final step, that final critical soak. And then the next thing I'll draw your attention to is they're going into a vacuum cool. And this is real common in a lot of brazing applications where, the braze is wet, and now we don't want to blow it around with a force cool. We want to do a little bit of vacuum cool and let the braze solidify before we go into an actual quench, which you're seeing right here. But in this case, they are going 1, 2, 3, 4. They're going 4 hours of vacuum cool, and they're vacuum cooling down to, I have the temperature here, down to 1,200 degrees from 2,000 degrees. So that's a very long time. The braze is definitely solidified at that point. And they don't have to wait that long before they go into this quench. They could have done that sooner and potentially shaved off a couple hours. So just by looking at this recipe, we can take 2 or 3 hours out of here pretty easily. Now, this takes some trial and error. So you might go back to your plant and you might try to shorten some of these things, and you might find that it adds distortion to your parts or adds stress to your parts, or there's negative side effects. And that's part of this. That's part of the trial and error to optimize your recipes. But if you're just doing the recipes the way you've always done them and you're not testing them to see if you can get efficiencies, then I would encourage you to do that, because that's where some of your biggest savings with no cost are going to come from. So this is a typical hardening cycle of tool steel here. And the thing I'm going to draw your attention to, and this is, I should note, this is temperature on the left. However, this is not time on the right. So this is every segment in the recipe here is evenly spaced. So this is a little distorted when we think about like ramp rates and stuff, because there is no x-axis there. But what I wanted to show you guys is, let's say you are running M-series or you're running some tool steels that temper at a high temperature. You could go straight into your tempers in the vacuum furnace right after your hardening process. And you can set that up in a single run. You don't need an operator to come over and check on the parts and then go into the recipe for the vacuum temper and then proceed to do that 3 times. You can have it set up in the software so that you do your hardening process right here. You go into your quench, and you can use the work thermocouples to say, I need to make sure these parts quench all the way to 150 degrees or 200 degrees or whatever you want them to go to. And then once all the work thermocouples are there, you can then evacuate the furnace, vacuum down, heat up, and do your double or triple tempers depending on what alloy you're running. And so some people in the room will say, hey, that's a poor use of time with a vacuum furnace to be running it at 1,000 degrees. It's a high dollar piece of equipment, and maybe I want to run it in a nitrogen temper or something like that. And that's something you guys have to weigh. If you have extra capacity in your furnace and you're able to run it like this where an operator can walk away for a very, very long cycle and that furnace can operate in a totally automatic function, then you're saving time, right? If you're not actually using your furnace 24/7. Now, if you have hardening work 24/7 for your vacuum furnace, then maybe it makes more sense financially for you to pull the parts out and put them into a nitrogen temper or something like that. But this is, for a lot of people who are not running at capacity, this is a great way to save on your operator's time while he can be doing something else. Power control units, and really what I'm getting at with this is power output from the transformers. So when we talk about optimizing our furnaces and optimizing our heating rates and getting the most out of them that we can, something that we see people do wrong all the time is power output from the transformers. And this can be even with the old rheostats, right? So I can't tell you how often we go into a company and they've tuned their furnace for a temperature uniformity survey, and let's say they do have rheostats, and you go look at the rheostats and not one of them is set at 100%. You've got one at 90, you've got one at 82, you've got one at 78 or something like that, right? Well, if you don't have your coldest zone set to 100%, you can never achieve max output from your transformers, right? So the proper way to do this, whether it's digital or whether it's through rheostats, the proper way to do this is always to have your coldest zone set at 100% output. And if you have it set at anything other than 100%, you're sacrificing power from your transformer that you could otherwise have. That applies to rheostats, that applies to digital power control units, no matter what you're doing. So the coldest zone should be 100% output. And then what we do is we trim back the other zones to get uniformity throughout the entire load. So people spend a lot of time tuning their furnaces with old rheostats. That's because you have one set of trim settings for your entire temperature range. Whether you're doing H900 at 900 degrees, whether you're doing M series at 2265, you have one set. You're not going to go in the control panel and adjust your rheostats mid-run. That's all you get. So with digital power control units, you can have as many settings as you want. So it's set up standard with 5 different temperature ranges. This one here is showing 4. But standard is 5 different temperature ranges. So you can have different trim values to get your temperature uniformity at 900 degrees, at 1500 degrees, 1800, 2000, you name it. They can all be different settings right here. And that's going to save you a ton of time when you're trying to survey, especially if you're somebody that has to stay in compliance with AMS 2750. That will be a really, really big time saver. The last thing I'll touch on is a lot of times when we have these digital power control units, we also get this where you can change the output during ramp. Now, are there business cases for having anything other than 100% during ramp? Yes, there might be. Let's say you've got really light, thin parts with high surface area, and they're going to come into soak very quickly, and you want them to come in somewhat uniform with temperature uniformity. Then you might actually tweak these. But if you're running any parts with any kind of mass to them, you should really have those all at 100%. So when you're advancing from one step to the next, you can have maximum power output in all of your zones. If you don't do that, you're again limiting yourself on the amount of power potential you have in your furnace, and you don't want to do that. Because we generally don't care about uniformity during ramp, we only care about it during soak. Again, there's a few caveats to that if you have light, thin parts that are going to come into temperature really quickly. All right, so furnace configuration. This is another one. It's not something you can do readily after the fact, but if you're thinking about your next furnace and how do I optimize my cycle times and get the fastest possible throughput, you should think about furnace configuration. Things like, do I use convection heating? Do I have end heating elements? Do I have a all-metal hot zone versus graphite? Do I have moly heating elements versus graphite? Do I have a 2-bar versus 6-bar? Those type of things are going to affect your runtime on your parts and get you more throughput. So the one thing I'll draw your attention to on this is going to be convection heating. So if you're running really dense loads of very heavy parts, it is really hard to beat the speed increase in your cycles with convection heating when done properly. So if you have a truly sealed hot zone, a truly gas-tight hot zone, convection heating can reduce your heat up times by as much as 30%. So now, if your hot zone is not truly gas-tight, you're not going to see that 30% yield on convection heating. And convection heating is much more efficient and faster between ambient room temperature and 1600 degrees. And it's not linear. It starts to taper off the efficiency between convection heating and radiant heating as we approach that 1600 degrees. So somewhere after 1250, it starts to slow down quite a bit until we get to that 1600. But in that first 1250 and up to that 1600, there can be considerable savings there with a convection heating system. So the way this works, we load the parts, we vacuum down, and then we backfill the furnace with up to 2 bar of nitrogen or argon. We circulate it with that fan there, and that's allowing all those gas molecules to pick up the heat from the heating elements and transfer it to the parts. When we talk about normal vacuum furnace heating, it's radiant heating, and all we have is the ability of the elements to glow and transfer the heat to the parts the way that the sun heats the earth through space. It's the same concept, right? But this is going to be more efficient at those lower temperatures. Now, there's some drawbacks to convection heating, too, and I see some faces in this room that have experience with it. You introduce leaks to your vacuum furnace because they're water-cooled motors, so that's another spot you can get water leaks. Water leaks in a vacuum furnace can be very frustrating trying to find them if they're small leaks. They can be very catastrophic if they're big leaks. They can destroy your hot zone. It's more maintenance on the motor. So now you have another motor you have to worry about, windings and bearings and grease, and what if it goes out, and what if my process is built around convection and I'm waiting for it to be replaced or rebuilt, and all of those things. There's more penetrations in the door, more spots for air leaks. So there are drawbacks to it as well. But if you're running big, heavy loads, it's hard to beat. Here is an example of 2 very similar loads. I'm going to call them the same loads, but stuff might be off by an inch or 2 here. One was run with convection, one was run without convection. And yes, these are two different furnaces. You'll see it right down there, 12 bar and 6 bar, but we're not talking about the cooling portion here of this run save time. We're only talking about the heating portion. And when we ran these two loads, here's the test results. On the heating time alone, we had a 4-hour time savings with convection versus not using convection. So if you have low density, high surface area parts, you're not going to see that kind of savings. If you have high density, low surface area parts, that's the kind of savings that you can potentially have with convection heating. It's not something that can be easily retrofitted onto an existing furnace in most cases, but if you're thinking about adding equipment to your fleet, adding to your facility, it might be something that you want to consider depending on the type of parts that you're going to run. So we talked about a lot today, and in summary, you can save money through automation in a lot of different ways. And it can be through reduction in labor costs, it can be in increasing uptime on furnaces and not having downtime while we're waiting on parts to be loaded. It can be in saving time on your AMS and your NADCAP audits and where your data is stored and keeping track of all your records for that. It can be in just process development, something that doesn't take any cost. You can go back to your plant and you can start doing this today. So there's a lot of ways, and these are just some of the ways that you can potentially decrease your operating costs, decrease your labor cost, and take some of these ideas back with you to your facilities when you're thinking about developing and improving your heat treat operations. So that's all I had. Any questions for me? You're welcome to see me afterwards too. Yes.
You spoke about recipe optimization.
Yes.
How does that really optimize the process wherein it's mixed batches, mixed tools in a bigger furnace?
Yeah, if you're
it's a variety of sizes, geometries.
Yeah. If you're mixing tools, the thing I would encourage you to do is you'd have to pick out your largest part, and you'd have to have a comparable work thermocouple in that part. And it's going to be a little bit less trial and error, and it's going to be more automation. So what you're going to do, you either put a thermocouple in the largest part or in a slug that's about the size of the largest part. Figure out where you're comfortable with your dead bands. When we talked about, do I wait for my parts to soak into plus or minus 10 degrees, or can I advance to the next segment when they're at plus or minus 15, plus or minus 20 degrees? So if you lower that dead band, the tail of your parts soaking in is going to be a lot shorter, and your cycle is going to be a lot faster. And you don't have to do it through just strictly human interface, right? You can let the machine decide that. You can say, I'm comfortable advancing to my critical soak once I get to plus or minus 25 on my final step. And then your final soak, you would set up and say, I need that thermocouple in that biggest part because I've got mixed tools now. I need that thermocouple to be in range before I start the timer on my austentizing, assuming you're doing a hardening cycle or whatever you're doing. So that's the way that you would do that. It'd be more through the use of work thermocouples and the guaranteed soak function, and then really looking at your dead bands. Do I need it to be plus or minus 10, or can it be a bigger window? And that's how you could maybe optimize it when you have mixed tools. And that's something a lot of people run into, because especially commercial heat treaters, they run whatever they get in. If everything is similar alloys, maybe different sizes and geometries, it's going in together if it's at a similar critical soak, and that would be the way to approach that. Yes, sir.
I'm just wondering, do you have any recommendations? You're talking about a system where, or a situation where the part has widely varying material thicknesses throughout, and through the whole cycle, the variation between those thermocouples, low thermocouples, is crucial.
So this is one single part with multiple pieces coming off of different thicknesses? Oh, okay. I'm not a metallurgist. I'm sure we have a few in the house, but probably what you'd want to do is come in right below the austentizing temperature and let it soak really, really good to make sure you have the highest mass part ready to go. Bring it up to its critical soak temperature, because what you don't want to do is you get up there prematurely, and now those thin parts sit at temperature too long and they have grain growth, and the thicker parts don't. They take a lot longer to come in, and so they don't have the grain growth, and now you get your part out and you have different grain sizes and distortion and all sorts of things. So when we're talking about our critical set points, whether it's hardening or brazing, we only want to be there as short as we possibly can. Because brazing, you don't want to have brazed runoff, you don't want to have too much vaporization of the braze if you're doing copper brazing. So a lot of naughty things happen if we stay there for too long. And it's the same with hardening. If we stay there too long, we have grain growth, which is not ideal either. So that's what I would do. And but that's tough if you have a part that has thin cross sections and large cross sections. The best way to handle that, you're going to have to do some trial and error. So.
Well, I mean, as far as automating, well, actually what I'm talking about would be mostly a yield. But we have to take for our manufacturer.
Yep.
Right now, some of our equipment's kind of aging, but right now, many of our processes have to be babysat.
Yep. I would look at what are they babysitting it for, and then try to find a way to automate that. So, like we could have, let's say you have a big part, depending on how big it is, you could have 10 or 12 thermocouples on one part, and you could say to the software, hey, I only need 9 of these to come into temperature. So I know this one part over here, this specific piece of the part lags, and I'm okay with that. I can live with that. So I need 9 of my 12 to come in, and once those 9 come in, advance to the next segment. So that might be an option, but without seeing the part in the process, it's hard to say exactly the best way to do that. But I would start by asking the operators or the engineer over the area, hey, why are you babysitting it? What could go wrong? And then look at, okay, how do we incorporate that into the software? And there are some things that just can't be automated, or they don't make sense to automate because it would be too challenging or it would introduce other risks. But for most people, there's a lot of things that can be automated and a lot of things that can be improved with some of this. So, yes.
I was going to say, in the interest of time,
Okay.
do you have your booth number off the top of your head?
I know when you walk in, it's 2 or 3 aisles to the left, and I will be there at, I think, either 12:45 or 1:45 today, and I will be walking around all day, so feel free to find me. Anyone at the booth will have my phone number. So if you stop by the Ipsen booth, they're happy to call. Give me a call and I can come over, and I can also hang out in the hallway if anyone has questions too. So.